Okay, so here is a video for class 18. We're doing external flow, and this is part 2. This is stuff coming out of Sengel's chapter 11, I believe. And this is, we're going to take a look at lift mostly today. So it's mostly going to be examples. Here's a picture wetted, and what I'm putting here is that he is in terminal velocity. Which is to say that he has reached a balance between his weight and the drag force that would be kind of spinning him. And drag force is kind of lift in this instance because he's pointing vertically. Just a reminder that when we use the area to base things, in this case it's the frontal area, right? It's the area that we could project in the direction of the flow. So lift, in the same way as drag, we can calculate by finding the lift coefficient and then rearranging it and applying it there. And this is an experimentally determined coefficient that you could really kind of think of as a correction factor to the dynamic pressure that 1/2 rho v squared u squared is. A lot of times they'll use u for some reason, and then that dynamic pressure times the area, but it doesn't exactly work right. So this is the lift coefficient can be something. Generally, it's going to be less than 1, but as we've seen, there are scenarios for drag coefficient where a drag coefficient becomes greater than 1. Now, the lift coefficient is and drag coefficient, when it comes to airfoils, is very dependent on the angle of attack. It's also dependent on the shape of the airfoil in this case right here. And it's also the aspect ratio of these airfoils is an important thing. So you have the chord length and the wing length. I'm saying the wing length. Let me see if I can say that the right way. I think that shouldn't be wing length. I think that should be depth. Let me double check on that. I'm now all of a sudden what I have in my notes doesn't seem correct. So let me look at just 1 second. Okay, so I think I misspoke in class. I said I was talking about the chord length right here, but the aspect ratio is actually the wing length, right? So I might have misspoken and said it had to do with this height right here. So just bear that in mind, right? So here's various curves for the lift coefficient based on the angle of attack with different aspect ratios of wing aspect ratios. So excuse me for that. And notably that we have, and many of them have like a little peak to them. And it's right there, we could consider that the stall angle, right? So and you can picture kind of what a stall angle is if we kept changing the angle of attack. Right here we're showing the velocity at an angle, but usually it's actually the wind, the wing that's at an angle compared to the direction of motion. And if you increase that angle too much, all of a sudden it won't generate lift anymore. It'll be entirely a drag phenomenon. And using these figures right here, what we can do is with an angle of attack, we could find out what the lift is, and then using, well, this actually has an angle over here. Let me go to another figure. All right, so here's one for a, this is out of Sengel, and I have marked this thing up with a bunch of curves so I could get find out this information. So here's another set where you can find the angle of attack. Using the angle of attack, you can with a prescribed for this prescribed section, which is a I don't see where it is right there. I guess, well, I've written it out here on this. This is an NACA 23012, and that describes like the foil basic dimensions, right? And in this graph also has with a slotted flap and then a double slotted flap. So what you would do for an angle of attack, you would find for, let's say, for this configuration right here, you would find what the lift coefficient is, and then using the lift coefficient over here, you would find what the drag coefficient was. So that would be the procedure using those curves. Right? These right here come from Munson, and they're used slightly differently. One notable thing, okay, so this figure shows this as a spoiler. Some people would actually call this as a wing, and what those wings do on sports cars and race cars, these are usually upside down, and instead of generating lift, they actually they call it my anti-lift, or they're generating a downward force to help keep traction on of the tires onto the driving surface. I don't know if you've ever seen maybe those races where a poorly aerodynamically designed race car actually can lift up and up into the air and go flying. So we really would, even though we would like to reduce drag, sometimes we have to have a certain amount of drag using the aerodynamic devices that are actually pushing downwards so that that you maintain good traction, and it also helps with the handling of to have greater pressure down onto the driving surface. And once again, I don't think using the terminology spoiler is correct, but that's what they had out of the book right here. But it keeps the wheels in contact with the ground. Here's one where I took this off the internet. I saw somebody had a CFD, and well, as they were trying to describe the usages, the difference between the spoiler and the wing, the airfoil. I'm not 100% convinced with some of the explanations that go out. I think it's probably, I'm sure the spoiler is beneficial in certain speeds, but not all. And also other devices that are added onto there, like the skirts and that kind of thing. Those all work together to try to accomplish the mission of the aerodynamics here, which in most cases is to try to keep a good traction for handling. But you might receive, under some circumstances, a decrease in drag because of the spoiler. But I'm not 100% convinced that that's true. A lot of times the people will talk about how it'll change the turbulence or laminar and turbulent boundary layer. Well, that usually takes place like really early on, the laminar boundary layer. And so I don't quite buy some of the explanations that I've seen in videos on the internet. But anyway, I'm going to stop the video and go and do examples in a new video. So that was just an introduction to lift.